Let's look at OpenStax College Physics, Chapter 12, Problem 23. A. What is the pressure drop due to the Bernoulli effect as water goes into a 3 centimeter diameter nozzle from a 9 centimeter diameter fire hose while carrying a flow of 40 liters per second? B. To what maximum height above the nozzle can this water rise? The actual height would be significantly smaller due to air resistance. Alright, so let's write down our knowns and unknowns. We're told that a fire hose has a diameter, I'm going to call it D1, of 9 centimeters, and the nozzle that the water comes out of has a diameter of 3 centimeters, and the volume flow rate Q is 40 liters per second. And if we convert it from liters to cubic meters, we end up with 0.0400 cubic meters per second. So that's the volume flow rate in SI units. And in part A, we're looking for the change in pressure. In part B, we want the maximum height to which water will rise. So let's look at our equation sheet here. So what I have here is an equation for the volume flow rate. Now, since we're just dealing with water, we can drop the density out of this and end up with AV equals constant. So the area here times the velocity in here is equal to the area there times the velocity there. So we can draw this here. So we have cross-sectional area A1, we have velocity 1 here, and then we have a smaller cross-sectional area A2 and a higher velocity V2. But when we multiply these through, so the product of these two and the product of those two will give us the Q that the problem already gave us. So Q is A1 V1, and it's also A2 V2. So from that, I can figure out that V1 is Q divided by A1. So that is Q divided by pi D1 squared divided by 4. We're not given the radius, we're given the diameter. So that will be 4Q. So Q is 0.0400 cubic meters per second divided by pi times 0.0900 squared. So what I did here is I flipped this up. So this is where this 4 went. I didn't put it down here. When I multiply these things out, I end up with 6.29 meters per second. I do the same for V2. So now for V2, I'm not going to write the equation down, just the numbers. So I have 4 times 0.0400, that doesn't change, divided by pi. It's the radius that changes, or the diameter, 0.0300 squared. So when I plug in numbers, I end up with, or when I calculate this, I get 56.6 meters per second. Quite a big difference. So now, the problem actually asks us about the pressure drop, pressure difference. So they also hint at Bernoulli's equation, and that would be here. So we know that the pressure plus 1/2 rho v squared plus rho gy is constant. So the pressure, these quantities in this area is equal to these quantities in that area. So I will write that. So I have P1 plus 1/2 rho V1 squared plus rho Gy1 equals P2 plus 1/2 rho V2 squared plus rho Gy2. What is Y? Well, it's the height of the center of mass of this column. And we notice that for this instance, we have the same Y. So I'm going to cross those out. So now what I'm looking for is the pressure difference. So P1 minus P2 will be 1/2 rho V2 squared minus V1 squared. So that would be 1/2. Density of water is 1,000 kilogram per cubic meters. And then we have 56.6 meters per second squared minus 6.29 meters per second quantity squared. And we end up with 1.58 times 10 to the 6th pascals. So this is the pressure difference as the water goes from the hose into the nozzle. Now, in the second part, we are looking for how high the water will squirt above the nozzle. So the water is going to come out and go something like this. And we're looking for the height difference from the nozzle to here, maximum height. So we'll start with Bernoulli's equation again, and I'm going to call all of those variables 2, because that's what I had before, and I'll call these variables 3. So Bernoulli's equation then will be P2 plus 1/2 rho V2 squared plus rho GY2 equals P3 plus 1/2 rho V3 squared plus rho GY3. So let's try to evaluate these things. What is pressure 2 as the water exits the nozzle? Well, it's in contact with the atmosphere, so that means that pressure 2 is going to be the atmospheric pressure, and so is the pressure up here. So that means that P2 and P3 are the same. They are the atmospheric pressure, so I'm going to cross those out. Then the other thing that we're told is that the water reaches the maximum height. That means that the velocity at that point is 0, so I'm going to cross this out. So I'm left with rho GY3 minus Y2 is equal to 1/2 rho V2 squared. I can divide through by rho and get the height difference, or H max, to be V2 squared divided by 2G. So that was 56.6 meters per second squared divided by 2 times 9.8 meters per second squared. And then we plug in the numbers to get 163.4 meters. So that's pretty high, but as they say, it's actually not as high as we're getting it here.